The Big Bang a birth cry that filled the newborn cosmos with light, heat, and expanding space. But the more we look, the more that simple picture begins to tremble. The evidence of an expanding universe is real. The ancient glow of the cosmic microwave background is real. The traces of the first elements are real, yet none of them actually prove that the Big Bang was the very first moment of everything. They only show us how far back our current physics can see. Beyond that horizon, the trail dissolves and the familiar laws that describe planets, stars and galaxies lose their strength. If the beginning is not truly the beginning, then the question changes. Not what happened at the Big Bang, but something far more unsettling. What existed before time could tick, before space could stretch, before the universe could even have a name. To understand why the Big Bang may not mark the true beginning of everything, we first need to clarify what the Big Bang actually represents. It is not a story of a fireball exploding into empty darkness. It is not a shower of fragments racing outward from a central point. There was no surrounding void, no outside space, no cosmic stage waiting to be filled. The Big Bang is the name we give to the earliest era of the universe that our physical laws can still describe. It marks the point where space itself began expanding, carrying matter and light along with it. The galaxies are not flying through space like sparks from a flame. Instead, the space between them stretches, increasing the distance the way ink dots separate when rubber fabric is pulled. This idea sounds abstract, yet it explains the first and most striking clue. The farther a galaxy is, the more its light is shifted toward the red end of the spectrum, showing it is receding. Edwin Hubble first noticed this nearly 1 century ago, and since then countless measurements have confirmed it. The universe is not static. It swells, it grows, it changes with time. This expansion leads naturally to a powerful image. If everything's moving farther apart now, then in the remote past everything must have been closer together. Wind the cosmic clock backward and stars gather into clusters. Clusters fall into clouds. Clouds condense into plasma, and temperature climbs to unimaginable levels. Eventually we reach an epoch so dense and hot that atoms could not exist. Then an earlier stage where even atomic nuclei could not survive. Push farther still, and we arrive at a time when the entire observable universe was compressed into a state far smaller than any star glowing with a heat beyond comprehension. This reconstruction of the past is not guesswork. It matches another piece of evidence. The universe today contains the exact proportions of hydrogen, helium, and deuterium that would have formed in such a furnace when the cosmos was only minutes old. These light elements are a fossil signature, a chemical memory imprinted before galaxies ever formed. Their abundance is one of the pillars supporting the Big Bang framework, but the most haunting evidence of all fills the sky not with stars but with a faint afterglow. It is a whisper of ancient light stretched into microwaves by billions of years of cosmic expansion. This glow comes from a moment when the young universe finally cooled enough for electrons to bind to nuclei, allowing light to travel freely for the first time. Today, that ancient radiation arrives from every direction uniform to a degree so astonishing that it reshaped cosmology. It is called the cosmic microwave background, and sensitive instruments have mapped it with exquisite detail. Its temperature is nearly the same across the sky, yet contains tiny fluctuations that later grew into galaxies, clusters, and filaments. It is a portrait of the universe in its infancy, a snapshot from a time long before stars ignited. No other model has been able to explain this cosmic relic with the same coherence as the Big Bang picture. Still, even with all this evidence, one fact must be repeated clearly. None of these observations show that the universe began at a precise moment of creation. They only show that the universe was once denser, hotter, and smaller. They reveal the limit of our current theories, the boundary beyond which our equations lose meaning. The Big Bang, as scientists use the term, does not describe the birth of space and time. It describes the earliest interval we can reconstruct by extrapolating known physics. Beyond that, the trail grows thin. Our instruments cannot see further. our mathematics becomes unstable. The laws that guide planets, stars, and galaxies cease to apply in the same familiar form. Some imagine this boundary as a curtain, some imagine it as a wall, some imagine it as a veil of ignorance waiting to be pierced. Yet in truth, it may be a horizon woven into the fabric of reality itself. This is the subtlety that often goes unnoticed. The Big Bang model is remarkably successful, yet it is silent about any earlier chapter. It does not claim to answer what preceded it. It does not rule out a phase before expansion began. It does not deny the possibility of cycles, bounces, previous universes, or deeper structures. It simply stops where our tools fail. That stopping point has misled many into believing the Big Bang is synonymous with the origin of everything. But the evidence does not demand that interpretation. It leaves room for something before, or perhaps something beyond the concept of before. It leaves us standing at the threshold of a mystery that becomes sharper the more we learn, and it invites the question that will carry us into the next part of our journey. If the Big Bang is not the true beginning, then what could lie on the other side of that horizon waiting in the dark where our equations fall silent? If we continue winding the cosmic clock backward, the familiar structure of the universe unravels step by step. Galaxies dissolve into swarms of stars, stars break down into clouds of plasma, and the great filaments that span hundreds of millions of light years fade into a fog of particles bathed in rising heat. Time itself seems to tighten as events crowd closer together. What now feels like unimaginable stretches? The birth of the first stars, the assembly of galaxies, the ignition of quasars shrink into brief sparks on the timeline. The universe becomes younger, denser, and smoother with every leap back. Eventually we reach an era where no star has yet formed because the heavy elements needed for planets, oceans, and life do not exist. Push deeper still, and the fog becomes so hot that even atoms are torn apart, leaving only a glowing sea of nuclei and electrons unable to join. This picture is not speculation. It is drawn from physics tested in laboratories, from particle accelerators, from nuclear theory, and from the relic light that still surrounds us. But the clock can rewind further. We reach a moment when even nuclei cannot survive. Protons and neutrons themselves melt into a quark-gluon plasma, a state so extreme that no solid analogy applies. Density rises, temperature climbs, and the size of the observable universe shrinks to something far smaller than any star we've ever seen. The cosmos is now a cauldron of fundamental particles colliding with energies beyond anything achievable on Earth. The laws of nature still guide this inferno, but they begin to strain. The forces that shape matter behave differently under such crushing conditions, and physics becomes a landscape of shifting equations. Even so, the journey backward has coherence. Each step is anchored in theory, observation, and experiment. We can trace the history of the universe all the way back to a fraction of a second after the moment we call the Big Bang. Yet just past this threshold, certainty begins to blur. We encounter energies so vast and densities so extreme that our best description of gravity, the theory of general relativity, collides with the rules of quantum mechanics. One governs the large, the other governs the small, and neither knows how to speak the language of the other. The curvature of space becomes immense, the quantum fluctuations of fields become dominant, and the mathematics ceases to produce reliable answers. Instead of offering a clear picture of an earlier state, the equations point toward infinities, quantities that should never appear in a physical theory. These infinities are the signposts of failure, the mark that our framework cannot pass through this region intact. It is here that the notion of a singularity emerges not as a real object in space, but as the breakdown point of our understanding. This is the cliff edge of cosmology. We can reconstruct the universe back to moments unimaginably early, but not all the way to a moment of absolute origin. We can describe the fire, the cooling, the formation of structure, the spreading of galaxies, but we cannot describe the supposed instant before space and time took shape. The deeper we push, the more obvious it becomes that the Big Bang is not a complete explanation. It is the earliest chapter written in language we can read, while the pages before it are written in a script no one has yet deciphered. This realization changes the question in a profound way. Instead of asking when the universe began, we're driven to ask why our theories fail at the boundary, and what kind of physics might extend beyond it. To rewind the clock further, we would need a theory that unifies the quantum world with gravity, a theory capable of describing space and time when they are compressed into scales far smaller than any particle. Such a theory might reveal that the singularity never existed, that the universe never collapsed into an infinitely dense point, and that the beginning we imagined was simply an artifact of pushing our equations past their domain. It might show that the universe emerged from a previous state, or oscillated through cycles, or rebounded from a collapse, or condensed from a fluctuation of a deeper vacuum. Or it might show that the very idea of before is meaningless, and that time itself is a property that arises only after the fabric of the cosmos cools into stability. Standing at this edge, one truth becomes clear. The failure of our theories is not a void, it is an opening. The breakdown of our equations is not the end of inquiry, it is the doorway to the greatest mystery in cosmology, and that doorway invites the next step in our exploration, confronting the singularity itself, the place where our understanding fractures and where new physics must begin. At the boundary where our understanding falters, the word singularity often appears, carrying with it an air of finality. In everyday language, it sounds like a point of ultimate concentration, a place where everything is squeezed into a speck smaller than imagination. But in the language of physics, the singularity is something very different. It is not an object, not a particle, not a seed of creation. It is the signal that our equations have been pushed past the limit of their validity. When general relativity is applied to a universe compressed into an unimaginably tiny volume, its mathematics predicts that density, temperature, and the curvature of space-time rise without bound. These infinities are not features of reality. They are evidence that the theory has been asked to describe conditions it was never designed to handle. The singularity is therefore a crack, not a cornerstone. It marks the place where gravity must become quantum, where space-time must have a structure more fundamental than the smooth continuum that Einstein envisioned. This distinction matters because it changes the meaning of the Big Bang itself. If the singularity is not a real physical state, then the Big Bang is not a moment when the universe emerged from an infinitely dense point. Instead, it is the first moment in cosmic history where our current theories produce reliable predictions. Everything before that is hidden not because it did not exist, but because our tools cannot penetrate it. The universe may have had a prior phase, or a prior form, or a prior geometry, yet general relativity cannot describe it. Asking that theory to reveal what lies beyond the singularity is like asking a microscope to show the surface of a distant star. The failure tells us nothing about the universe, only about the instrument we're using to examine it. In this sense, the singularity is an invitation to seek a deeper theory, one that unifies quantum mechanics and gravity into a single framework. Quantum mechanics governs the world of the small, where particles behave like waves, where uncertainty rules, and where energy fluctuates even in apparent emptiness. General relativity governs the world of the large, where mass shapes spacetime and spacetime guides motion. In the everyday universe, these two realms coexist without conflict. But in the earliest moments of cosmic history, the small and the large were intertwined. The universe was tiny yet massive. The curvature of spacetime was extreme, yet quantum fluctuations dominated. In that regime, neither theory alone is sufficient. Their equations contradict one another, and attempts to merge them using classical mathematics lead to contradictions, infinities, and breakdowns. This conflict is the heart of the singularity problem. It reveals that our current view of spacetime is incomplete. It hints that space and time might not be continuous but granular. It suggests that geometry itself may emerge from deeper processes the way temperature emerges from the motions of countless molecules. Physicists have spent decades searching for a theory that can resolve this conflict. Some approach the problem by trying to quantize gravity directly. Others propose that space-time is woven from discrete loops forming a network so fine that it appears smooth at large scales, but becomes granular at the smallest distances. Still others suggest that the fundamental entities are not particles but vibrating strings or multidimensional membranes. Each of these efforts is motivated by the same need: to remove the singularity not by smoothing it over, but by replacing it with a description that remains finite, well-defined, and physically meaningful. In many of these approaches, the universe does not collapse to an infinitely dense point. Instead, it reaches a maximum compression, then transitions into a new phase. The singularity becomes a bridge or a bounce or a transformation. It ceases to be an end and becomes a boundary between eras. This possibility reshapes the narrative of cosmic origins. If the singularity is removed, then the question of what came before the Big Bang may have an answer that lies within the domain of physics, not philosophy. The universe may have contracted before it expanded. It may have existed in a timeless quantum state. It may have been part of a larger structure that undergoes cycles, or it may have emerged from a fluctuation of a deeper vacuum. Each of these ideas carries different implications for the nature of time, for the evolution of space, and for the ultimate fate of the cosmos. But all of them share a common root: the rejection of the singularity as a physical reality. To stand at the edge of the singularity is to stand at the edge of our knowledge. It is to look into a region where our symbols fail and our frameworks collapse. Yet it is also to glimpse the next frontier of science. The singularity marks the place where new physics must begin. It is the crack through which the light of a deeper understanding may enter, and it leads us to the next step in our journey, examining why the very question of before the Big Bang may be both meaningful and misleading depending on how we define time itself. When we speak about what happened before the Big Bang, we are borrowing a word from everyday experience and applying it to a realm where its meaning may not hold. In ordinary life, time is a river that flows in one direction. There is a past, a present, and a future. We remember what came before, we experience what is now, and we anticipate what lies ahead. This intuition is so deeply rooted that it feels impossible to imagine anything else. Yet physics has shown that time is not a universal backdrop. It bends, it stretches, it slows near massive bodies, and it links inseparably with space to form a single fabric. In this fabric, time does not exist independently. It is shaped by the geometry of the universe. And if the geometry of the universe has a boundary, then time may have a boundary as well. This is why the question of what came before the Big Bang can be misleading. It assumes that time existed prior to the event ticking forward like a clock waiting for the universe to appear. It assumes a stage on which the cosmos could enter as if the curtain was simply closed until the moment of ignition. But if time and space emerged together, then there was no earlier moment. There was no empty theatre. There was no waiting frame. Asking what happened before the Big Bang would then be like asking what lies north of the North Pole. The question sounds sensible, but the answer reveals a flaw in the premise. The map ends not because something is hidden beyond the edge, but because the coordinate system itself ceases to apply. Yet this does not mean the question is useless. It has value precisely because it exposes the limits of our assumptions. When cosmologists point out that time may have begun with the Big Bang, they are not dismissing curiosity. They are tightening the definition of the words we use. If time is a property that arises from the structure of space-time, then asking about a time before space-time may simply be incoherent. But if there is a deeper level of reality where a different kind of time exists, then the question might still have meaning. This is where new theories diverge. Some insist that time has a first moment. Others propose that time extends through previous phases. Still others argue that time is emergent like temperature, and only becomes meaningful at large scales. The danger is not in the question itself, but in mistaking intuition for evidence. Human imagination evolved to navigate days, seasons, and lifetimes, not cosmic epochs. We experience time on a scale where its direction and continuity feel absolute. But the universe has shown again and again that our intuition is a poor guide to fundamental reality. The Earth feels motionless, yet it spins. The sun seems to circle the sky, yet the Earth orbits it. Space feels flat, yet it curves. Time feels uniform, yet it flows differently near massive objects. If time can stretch and slow, then it can also begin. And if it can begin, then the idea of a time before the Big Bang may simply be a projection of our habits of thought, not a reflection of the cosmos. Still, there is another possibility. The failure of our theories near the supposed beginning may indicate not the start of time, but the need for a new description of time. Perhaps what we call the beginning is merely a transition, the way water becomes steam or ice melts into liquid. In such a view, the Big Bang marks a change in the behavior of space-time, not the start of existence. Time before this transition might have flowed differently or been defined in another way altogether. This raises profound questions. Could the universe have undergone a contraction before expanding? Could it have passed through a state where time lost meaning and then regained it? Could there be remnants or signatures of an earlier epoch encoded in the structure of the cosmos we see today? These possibilities are not idle speculation. They form the basis of several scientific models that attempt to extend our understanding beyond the apparent beginning. Some suggest that time loops through endless cycles. Others propose that the universe rebounded from a prior collapse. Still others imagine a realm where quantum fluctuations give rise to space-time itself. Each of these models treats the Big Bang not as a first moment but as a doorway. And to explore these doorways we must loosen our grip on intuition, while holding tight to evidence. The question of what came before the Big Bang is therefore both meaningful and dangerous. It is meaningful because it drives the search for deeper theories. It is dangerous because it tempts us to use familiar language to describe unfamiliar reality. To move forward, we must recognize the boundary between what our ideas suggest and what our observations support. We must refine the question, not abandon it. And when we do, a remarkable landscape opens. Beyond the singularity, beyond the apparent beginning, lie 7 major hypotheses that attempt to describe what preceded the Big Bang, or what replaces the notion of a beginning altogether. Some of these hypotheses claim that there was nothing before. Some claim there was a universe before. Some claim that time itself is cyclical. Some claim that our universe is one bubble among countless others. Some claim that space and time emerge from deeper structures. Each one offers a different vision of reality. Each one attempts to answer the same riddle. And each one brings us closer to understanding whether the Big Bang was a true beginning or merely a chapter break in a much longer cosmic story. Our journey now turns to these possibilities. The first is the most austere, the most subtle, and in many ways the most challenging to intuition. The idea that there was no before because time itself begins with the universe. The idea that there was no before the Big Bang may seem like a refusal to answer the question, yet it is rooted in one of the most profound insights of modern physics. Time is not an independent backdrop against which the universe unfolds. It is a feature of the universe itself. In everyday experience, time feels absolute. Clocks tick at the same pace. Events follow one another in a fixed order. But experiments and observations have shown that time can slow near massive bodies, accelerate in regions of weaker gravity, and stretch with motion. Time is inseparable from space, and together they form a single fabric that curves, bends, and evolves. If that fabric comes into existence at the Big Bang, then time comes into existence with it. In this view, asking what happened before the universe began is like asking what happened before time existed to measure it. This perspective arises naturally from general relativity, which describes gravity not as a force, but as the curvature of space-time. According to this theory, the geometry of space-time tells matter how to move, and matter tells space-time how to curve. Time is not a universal river flowing through all of reality. It is a direction within the fabric of space-time, and that direction is defined by the structure of the universe itself. When cosmologists trace the evolution of space-time back to the earliest moments, the geometry becomes so compressed and curved that the concept of time loses meaning. There is no earlier direction to point, no timeline to extend, no coordinate that can be labelled before. In this framework, the Big Bang is not an explosion in time, it is the boundary of time. This is a difficult idea to absorb because human intuition insists that everything must have a cause, and every cause must have occurred earlier. Yet causation is a feature of time, not a law imposed from outside. If time itself has a finite extent, then causation cannot be extended beyond that extent. The question what caused the Big Bang may therefore be unanswerable, not because the answer is hidden, but because the question assumes a structure that does not exist. Just as there is no point north of the North Pole, there may be no moment before the first moment of time. The comparison is not a metaphor, it is a direct analogy from geometry. The North Pole is not the edge of the Earth, it is the point at which the coordinate of latitude stops being meaningful. Likewise, the Big Bang is not the edge of existence, it is the point at which the coordinate of time stops being meaningful. This viewpoint is sometimes mistaken for a claim that the universe emerged from nothing, but that interpretation goes beyond what the physics asserts. The framework does not describe creation, it simply describes the limits of the mathematical system used to model space-time. It states that time cannot be extrapolated beyond a certain point. It does not speculate about what might exist outside that framework. It offers a boundary condition, not a narrative, and yet for many cosmologists this boundary condition is appealing because it avoids the need to imagine a pre-existing state, a cause or a prior universe. It is a minimalist answer, reducing assumptions rather than multiplying them. Still, the idea that time has a beginning raises challenging implications. If time began with a Big Bang, then the universe has a finite age. But what does it mean for something to have an age when there is no external reference? Age is measured by the passage of time, and if time begins at the Big Bang, then the universe has existed for as long as time has existed. The two concepts become identical. In this sense, the universe is not young or old relative to anything else. It simply exists within the only temporal framework available. This conclusion can feel unsatisfactory, not because it is scientifically weak, but because it contradicts our instinct that there must be something beyond the boundary, some deeper origin waiting to be unveiled. The strength of this hypothesis lies in its simplicity. It requires no additional dimensions, no cycles, no quantum bounce, no multiverse, and no pre-existing substrate. It fits within the structure of general relativity and remains consistent with all current observations. It does not invent entities that cannot be tested. It does not add layers beyond necessity. For these reasons, many physicists regard it as the most conservative interpretation of the Big Bang. But its weakness lies in the very same qualities. It provides no deeper story. It offers no mechanism. It satisfies the equations but not the imagination. It closes the question rather than extending it. And for a field driven by curiosity, that closure can feel like a wall rather than a window. Yet even within this framework, cracks appear. General relativity describes space-time as smooth and continuous, but quantum mechanics suggest that reality at the smallest scales is granular and fluctuating. If space-time itself is subject to quantum behavior, then the concept of a boundary to time becomes less certain. Quantum fluctuations do not respect classical boundaries. They blur edges, smear limits, and introduce uncertainty. Time might not end abruptly at a single moment, but fade into a region where its meaning dissolves gradually. This possibility leads to a bridge between the idea that time has a beginning and the idea that something preceded the Big Bang. It opens a path toward models that extend the timeline without contradicting observable physics. For now, the hypothesis that there was no before remains both elegant and incomplete. It reminds us that our questions carry hidden assumptions. It forces us to examine the foundations of our thinking, and it sets the stage for the next possibility models in which the universe did not begin but rebounded, cycled, or emerged from a prior phase. The next step in our exploration leads to a radically different vision, a universe that breathes expanding and contracting across epochs, with each cycle giving birth to the next. The notion of a universe without a before offers a stark and disciplined picture of reality, but for many scientists it leaves an unresolved tension. If time begins at the Big Bang, then the universe simply exists with no deeper context. Yet the cosmos does not feel like a self-contained statement. It evolves, it changes, it unfolds. Galaxies form and drift apart. Stars ignite and fade. Structures rise and dissolve. Everything we observe suggests motion, transformation, and progression. It is natural then to wonder whether the universe itself might participate in a larger cycle, a rhythm extending beyond a single expansion. This possibility forms the heart of the second great hypothesis, the idea that the universe may have undergone previous eras, that expansion may be followed by contraction, and that the Big Bang may not be a beginning, but a transition in an eternal sequence. The seeds of this idea were planted long before modern cosmology. When Einstein first applied his equations to the universe, he assumed it must be static, neither expanding nor contracting. But his own mathematics suggested otherwise. A universe filled with matter cannot remain fixed. It must either collapse or expand. For a time, cosmologists explored the notion that expansion might eventually reverse. Gravity acting across the vastness of space could slow the outward motion, halt it, and draw everything together again. In this picture, galaxies would drift closer. Clusters would merge, and over unimaginable stretches of time the universe would contract into a dense, hot state. From that collapse, a new expansion might arise, producing what we call the Big Bang. In this scenario, our universe is one cycle in a chain, and the arrow of time extends through each contraction and expansion. This concept, known as a cyclic universe, appeals to intuition in a way the boundary of time model does not. It satisfies the instinct that something must precede, that the cosmos must emerge from a previous state. It offers a narrative that feels organic. A star is born, burns, collapses, and sometimes triggers the birth of new stars. Why should the universe not behave in a similar way? The cyclic model also sidesteps the discomfort of a singular beginning. There is no first moment, no creation from nothing, no abrupt emergence of time. Instead, there is continuity, a cosmic heartbeat pulsing through eternity. The universe expands, then contracts, then expands again, perhaps endlessly. Yet to transform this appealing image into a scientific framework requires more than poetic symmetry. A cyclic universe must confront formidable challenges. One of the strongest involves entropy, the gradual increase of disorder. In every process we observe energy spread, structures decay, and disorder rises. If the universe has undergone countless cycles, why is there not an accumulation of entropy so overwhelming that no structure could form? Why are galaxies able to exist at all? This question haunted early versions of the cyclic model, suggesting that with each cycle, the universe would become more chaotic until the very concept of a new beginning would be impossible. Modern versions of the cyclic idea attempt to solve this problem with new physics. Some propose that entropy is diluted during contraction. Others suggest mechanisms that reset the thermodynamic state of the cosmos, and some draw upon theories beyond general relativity, invoking higher dimensions or new fields capable of draining or dispersing entropy. One influential proposal, inspired by developments in string theory, reimagines cycles not as simple expansions and contractions of a single universe, but as collisions between multidimensional brains, vast sheets of space-time drifting through a higher dimensional arena. In this picture, each collision releases enormous energy, igniting what we perceive as a Big Bang. When the brains separate, the universe expands. When they drift back together, another collision occurs, beginning the cycle anew. We will explore that idea more fully later, But even without such embellishments, the cyclic concept carries profound implications. If the universe has experienced previous eras, then remnants of earlier cycles might linger in the cosmic microwave background, in the distribution of galaxies, or in the geometry of space-time itself. Some researchers have searched for such signatures, hoping to detect faint imprints that survived the transition. So far, no decisive evidence has emerged, but the search continues and the possibility remains opener. The strength of the cyclic idea lies not in proof, but in plausibility. It offers a coherent alternative to a universe with a single beginning, and it highlights the possibility that time extends beyond the moment of apparent birth. Still, the cyclic hypothesis does not answer all questions. It shifts the mystery rather than erasing it. If cycles repeat, what governs the sequence? If contraction leads to expansion, what mechanism drives the rebound? If entropy is reset, what enforces the reset? And if the universe has no first moment, does time truly stretch backward forever? Or does the chain of cycles itself have an origin? These questions remind us that even elegant ideas must face the demands of evidence and consistency. A cyclic universe may solve the problem of a beginning, but it introduces a new set of puzzles, and yet it serves a crucial role in our journey. It demonstrates that the apparent beginning at the Big Bang is not the only way to interpret the evidence. It reveals that cosmic history might extend further than our theories currently allow, and it prepares us for the next hypothesis, one that takes the idea of a prior phase and grounds it not in cycles, but in the quantum structure of space-time itself. If the universe once contracted, perhaps it did not collapse into a singularity. Perhaps it reached a finite limit and then bounced, giving rise to a new expanding era. This is the next step in our exploration, the possibility that the Big Bang was not a birth, but a rebound from a universe that came before. If the universe truly moves through cycles of expansion and contraction, then traces of earlier eras might still be present in the cosmos we observe today. This idea has motivated numerous attempts to search for faint fingerprints left behind by a previous cycle. The most likely place to look is the cosmic microwave background, the ancient afterglow that blankets the sky. If the universe experienced a contraction before the current expansion, then subtle patterns could have survived the transition. Some researchers have claimed to detect circular imprints, temperature anomalies, or unusual alignments that might hint at a pre-existing phase. Others argue that these features fall within the expected range of random variation. The debate illustrates a deeper point. Looking for evidence from before the Big Bang is extraordinarily difficult because the processes that shaped the newborn universe tend to erase or blur information from earlier states. Even the large-scale distribution of galaxies has been examined through this lens. If the universe once collapsed, then the seeds of structure might bear signs of compression or asymmetry. Yet the observed arrangement of galaxies' filaments, voids, clusters, can be explained entirely by the physics of the current expansion, without invoking prior cycles. This does not rule out a cyclic universe. It simply means that any evidence must be subtle, buried beneath layers of cosmic evolution. The more time passes, the more thoroughly expansion stretches, smooths, and reshapes the universe. By the time galaxies form, most traces of an earlier era may already be beyond recognition. The cyclic idea therefore remains scientifically plausible but observationally elusive. There is another challenge. If contraction followed by expansion is a repeating process, then some mechanism must reverse the collapse. Gravity alone cannot accomplish this. Once contraction begins, it accelerates. Matter becomes denser, curvature increases, and temperatures rise. Nothing in classical general relativity prevents the universe from collapsing into a singular state. To avoid that fate, new physics must intervene, halting the collapse before it reaches an infinite density and igniting a new expansion. This rebound is the critical step, and it demands an explanation. Some proposals suggest that exotic forms of energy could counteract gravity at high densities. Others point to modifications of general relativity that become important at small scales. But the most developed idea comes from efforts to merge gravity with quantum mechanics. Quantum theories suggest that space-time may not be smooth and continuous. Instead, it may be composed of discrete units, woven into a network so fine that it appears seamless at ordinary scales, but becomes granular at extreme densities. In such a picture, space-time cannot collapse indefinitely. There is a minimum scale beyond which further compression is impossible. When the universe approaches this limit, quantum effects generate a repulsive influence that counteracts gravity. The collapse slows, halts, and reverses. The universe rebounds, expanding outward once again. This process is known as a quantum bounce. It replaces the classical singularity with a transition. Instead of a point where the laws of physics break down, there is a bridge connecting a prior contracting phase to our expanding universe. This idea reshapes the cyclic hypothesis into something more precise, rather than an endless series of expansions and contractions driven by classical gravity. The universe oscillates through quantum transitions that prevent singularities. Each cycle has a well-defined minimum size and the laws of physics remain intact throughout. The Big Bang becomes the moment of rebound, not the moment of creation. Time extends into the previous cycle, and the universe has a history that precedes the current expansion. This vision is compelling because it offers a concrete mechanism rooted in emerging theories of quantum gravity. It solves the singularity problem, avoids the need for a first moment, and provides a framework in which cycles are not merely poetic but mathematically grounded. Yet even this refined version faces questions. Does the bounce erase information from the prior cycle or allow some of it to survive? If information survives, could it be detected in the cosmic microwave background or in primordial gravitational waves? If it is erased, does the universe truly have a past in any meaningful sense? And if cycles stretch infinitely backward, does entropy accumulate or does quantum geometry reset it? These questions are not yet answered, but they mark the division between speculation and science. Theories that make testable predictions move forward, those that do not remain on the fringe. What makes the quantum bounce especially significant is that it paves the way for the next phase of our journey. The bounce is not the end of speculation about a prior universe. It is the beginning of a new class of ideas grounded in the belief that gravity must be quantized, that space-time has structure, and that the earliest universe can be described without infinities. In the next part, we will explore this idea more deeply, examining what a universe before the Big Bang might have looked like, if quantum geometry prevented collapse and allowed time to continue through the transition. The cyclic hypothesis opens the door. The quantum bounce invites us to step through it. And beyond that doorway lies a radically different picture of the cosmos, one in which the Big Bang marks not a beginning, but a turning point in a universe that existed before. To picture a universe that rebounds instead of collapsing into a singularity, we must enter a realm where the familiar description of space-time breaks down, and quantum effects take control. In everyday physics, gravity is the dominant force at large scale, shaping planets, stars and galaxies. But as the universe contracts toward extreme density, the quantum nature of matter and space-time can no longer be ignored. Particles fluctuate, fields jitter, and geometry itself becomes uncertain. In this regime, space is no longer smooth, and time is no longer continuous. Instead, space-time behaves like a lattice composed of discrete units that cannot be compressed beyond a certain limit. This idea emerges from attempts to build a quantum theory of gravity, most prominently loop quantum gravity, which proposes that space is woven from finite loops, forming a vast network. In this framework, the universe cannot shrink indefinitely. As the density of matter increases, the curvature of space-time rises, but it does not reach infinity. Instead, quantum geometry introduces a repulsive effect that counteracts gravitational collapse. The closer the universe comes to its minimum scale, the stronger this repulsion becomes until eventually contraction halts entirely. At that moment, the universe reaches a turning point, a smallest possible size determined by quantum structure. Then the process reverses. The universe begins to expand, driven not by an explosion, but by the release of compression energy accumulated during contraction. This rebound is smooth, continuous, and governed by physical laws. It replaces the singularity with a quantum bounce. The implications of this idea are profound. If the Big Bang was a bounce, then the universe existed before the moment we call the beginning. It had a prior history, a prior evolution, and a prior structure. Time did not start at the Big Bang. It passed through it. The boundary that once seemed absolute becomes permeable. The horizon of our understanding shifts back, revealing that the Big Bang may be a transition between two phases rather than a moment of origin. This transforms the narrative of cosmology. Instead of emerging from nothing, the universe emerges from a state shaped by quantum gravity. Instead of a singular creation, there is continuity across the deepest threshold. This picture raises questions that are both scientific and conceptual. What was the universe like during its contracting phase? Was it filled with galaxies like the present one? Was it smooth or chaotic? Did it resemble our universe in any way, or was it governed by different conditions entirely? Some models suggest that structure would have been erased during contraction, leaving a featureless state that blossomed anew after the bounce. Others suggest that information could survive encoded in subtle properties of space-time or carried by quantum fluctuations. If any of that information crossed the bounce, it might leave traces in the cosmic microwave background or in primordial gravitational waves. Detecting such traces would transform speculation into evidence. For now, the search is ongoing. Experiments are being designed to probe the earliest moments of the universe, looking for signatures that cannot be explained by classical cosmology alone. Future observations of gravitational waves may provide the first clues, because gravitational signals can pass through regions that erase other forms of information. If a bounce occurred, it might have generated ripples that still persist, faint but detectable with sensitive instruments. The possibility of discovering observational evidence for a pre-Big Bang universe has energized research in both theoretical physics and astronomy. It offers a chance to glimpse beyond the horizon of time. Yet even with its elegance, the bounce model carries uncertainties. Quantum gravity remains an unfinished theory. Its mathematical foundations continue to evolve, and competing approaches offer different predictions. Some suggest that space-time is discrete. Others propose that it emerges from entanglement patterns, and still others imagine higher dimensional structures underlying the observable universe. The bounce is compelling because it removes the singularity and preserves the continuity of time, but it depends on assumptions that have not yet been confirmed in experiment. Until a quantum theory of gravity is fully established, the bounce remains a possibility, not a conclusion. Still, it plays a crucial role in our exploration. It bridges the gap between the boundary of time hypothesis and models that describe a universe preceding the Big Bang. It demonstrates that new physics can extend the timeline without violating known observations, and it prepares the ground for an even more adventurous idea that the universe did not merely rebound but emerge from fluctuations in a deeper quantum vacuum, a realm where space-time itself arises spontaneously. To understand that possibility, we must look beyond cycles and bounces and examine the strange behavior of empty space and emptiness that is never truly empty. To explore the idea that the universe could arise from a fluctuation of a deeper vacuum, we must first overturn one of the most persistent assumptions in human thought, that empty space is truly empty. In ordinary language, a vacuum is nothingness. It contains no matter, no air, no dust, no light. But in quantum physics, emptiness is a seething arena of activity. Particles and antiparticles flicker into existence and vanish. Energy rises and falls in tiny bursts. Fields ripple with uncertainty. What appears silent is alive with motion. This restless undercurrent is a consequence of the uncertainty principle, which states that energy cannot be fixed precisely over extremely short intervals. Even in the absence of matter, the vacuum is never at rest. This peculiar behavior is not speculation. It has been measured in experiments observed in particle physics and confirmed in the behavior of atoms and fields. The forces that hold atoms together depend on fluctuations in the vacuum. The decay of radioactive particles is influenced by them. Even the acceleration of the expanding universe may be driven by vacuum energy. If the vacuum has energy structure and quantum activity, then it is not a void. It is a physical state governed by laws. And if the vacuum is a physical state, then it can change, transform, and give rise to new configurations. In this view, the universe may not have emerged from nothing but from a quantum vacuum, in which fluctuations occasionally produce conditions capable of expanding into a cosmos. The idea becomes more powerful when combined with inflation, the concept that the early universe expanded at an extraordinary rate driven by a field with high energy density. If a fluctuation in the vacuum produced a region where such a field existed, then that region could begin expanding rapidly. As it expanded, quantum fluctuations would be stretched across cosmic scales, seeding the formation of galaxies and clusters. When inflation ended, the energy would convert into matter and radiation, filling the universe with the ingredients of stars, planets, and life. The Big Bang would then be the aftermath of inflation, not the origin of existence itself. In this model, our universe is a bubble that formed within a larger quantum vacuum, a bubble that grew cooled and evolved. This picture raises a striking question. If one such bubble can form, could others form as well? If the quantum vacuum can spawn expanding regions repeatedly, then there may exist countless universes, each with its own physical constants, dimensions, or structure. Some might expand and cool like ours. Others might collapse quickly or remain barren. We would be one bubble among many, not the solitary universe, but part of a vast and possibly infinite ensemble. This is not a fantasy invented for dramatic effect. It arises naturally from quantum field theory and inflation. The same mechanism that could generate our universe could generate others. Yet the core idea does not require a multiverse. It simply requires that the vacuum is not absolute nothingness. In this framework, the question of what happened before the Big Bang becomes a question of what state the vacuum was in. Was it timeless? Did it fluctuate eternally? Did it exist in a higher dimensional space? Or did it undergo transitions the way water becomes ice or steam? Some versions of the hypothesis propose that the vacuum itself evolves. Others propose that it has always existed in its current form. Still others suggest that the vacuum is emergent from an even deeper reality, a mathematical structure or network of entanglement. This leads to an important clarification. When scientists say the universe might have emerged from a quantum fluctuation, they are not claiming that something came from literal nothing. They are describing a transition from one physical state to another, in a realm where the usual concepts of space and time may not apply. The vacuum they refer to is governed by laws, contains energy, and allows processes to occur. It is not a void in the philosophical sense. It is a medium in which space-time can arise. But this hypothesis, like the others, faces challenges. If our universe originated from a vacuum fluctuation, can we detect evidence of that origin? Could subtle imprints remain in the pattern of cosmic microwave background fluctuations? Could gravitational waves carry echoes of a quantum birth? Could the distribution of matter reflect processes from before inflation began? So far, no definitive signature has been found. The vacuum model provides a mechanism, but not yet a measurement. It explains how the universe could begin without a singularity, but it does not prove that it did. Still, it offers a compelling bridge between quantum physics and cosmology. It shows that the Big Bang may have been a transformation, not a creation. It demonstrates that the boundary between existence and non-existence is more subtle than intuition suggests. And it opens the path to a more radical possibility, that the universe we see is only one pocket within a larger structure, a single bloom in a field of cosmic flowers. Before we step into that idea directly, we must examine the theory that extends vacuum fluctuations into an ongoing process, where universes form endlessly in a vast expanding backdrop. That theory proposes a cosmos in which inflation never fully ends, and where new universes continue to appear like bubbles in a boiling sea. It is the next step in our journey, and it expands the question of what came before the Big Bang into a question of what surrounds it. The idea that our universe could be just one bubble within a far larger reality arises naturally when inflation is extended beyond its initial purpose. Inflation was first proposed to solve puzzles in cosmology. The remarkable smoothness of the cosmic microwave background, the near-perfect flatness of space, and the absence of relics predicted by earlier theories. By positing that the early universe expanded at an astonishing rate, inflation explained these mysteries with elegant simplicity. Space stretched so rapidly that any irregularities were smoothed away, and the observable universe became just a tiny patch of a vastly larger whole. But once the idea of inflation was accepted, a deeper realization followed. If inflation can occur once, it may occur repeatedly. If it can begin in one region, it may continue in others. And if quantum fluctuations affect the inflationary field, then inflation might never fully end. In this picture, the universe becomes a vast and expanding sea of inflating space. Within that sea, pockets occasionally stop inflating and blossom into bubble universes like our own. Each bubble begins with a burst of energy, expands, cools, and develops structure. Stars form, galaxies swirl, life might arise. Meanwhile, the surrounding space continues to inflate, pushing bubbles apart so rapidly that they can never collide or share information. New bubbles continue to appear in distant regions, each isolated by ever-growing expanses of inflating space. This is the idea of eternal inflation, a process with no global end generating universes endlessly. If this is true, then our universe is not the universe. It is a local region, one among countless others. The Big Bang marks the moment our bubble formed, not the beginning of everything. Time within our bubble flows forward from that moment, but in the larger inflating sea, time may flow differently, or not at all. Each bubble may contain different physical constants, different numbers of dimensions, or different forms of matter. Some bubbles might allow stars to form, others might remain featureless. A few might be suitable for chemistry, planets, and consciousness. We inhabit the bubble in which conditions allow us to exist, not because it was designed that way, but because observers can only arise where observation is possible. This perspective transforms the question of what happened before the Big Bang. It suggests that the Big Bang was the beginning of our local region, but not the beginning of the broader reality. What came before the Big Bang was more inflation. What surrounds our universe is more inflation. The same process that created our cosmos continues beyond our horizon, unreachable and unobservable, yet implied by the mathematics. In this view, the Big Bang is a local event in a much larger tapestry, yet eternal inflation raises deep uncertainties. If other bubbles exist, can we ever detect them? In most versions of the theory, the answer is no. The space between bubbles expands so rapidly that signals cannot cross it. Even if bubbles collide, the evidence would be erased or distorted beyond recognition. Some researchers have suggested that rare collisions could leave scars in the cosmic microwave background, faint circular patterns or directional asymmetries. Searches for such patterns have been conducted, but the results remain inconclusive. Some studies report hints, others find none. The ambiguity reflects the limits of our observations as well as the subtlety of the predicted signals. Another challenge lies in the nature of probability. If infinite bubbles form, then every possible configuration of physical laws may exist somewhere. How do we make predictions in such a landscape? How do we compare theories when all outcomes occur in some bubble? This problem, known as the measure problem, remains unresolved. It reveals a tension between mathematical beauty and scientific testability. A theory that explains everything risks explaining nothing. Despite these obstacles, eternal inflation remains influential, because it arises naturally from the physics of the early universe. It does not require invention, It is a consequence of the same equations that explain observations in our own cosmos. Whether or not other bubbles exist, inflation remains the leading explanation for the structure of the observable universe. The multiverse is the extrapolation, not the foundation. This distinction matters. We do not adopt the idea because it is appealing, but because it follows logically from the model that fits the data we have. Still, the multiverse interpretation invites humility. It challenges assumptions about uniqueness, centrality, and scale. It suggests that our universe may be one expression of deeper processes that operate beyond our reach, and it raises a possibility even more striking that the story of our universe is not isolated, but part of a larger evolutionary landscape in which universes emerge, expand, and drift beyond each other's horizons. The next step in our journey takes this notion further into a domain where the structure of space is not merely inflated but shaped by extra dimensions and higher dimensional surfaces called branes. In that vision, the Big Bang is not the birth of a bubble, but the consequence of a collision between immense sheets of space-time moving through a higher realm. To understand that idea, we must shift our imagination once again from bubbles floating in a sea to brainies gliding through dimensions beyond our perception. To imagine a universe shaped by higher dimensions, we must once again stretch beyond the limits of ordinary intuition. Our senses tell us that space has 3 dimensions: length, width, and height, and that time flows as a 4th. But the mathematics developed to unify the forces of nature hints at something more. In these theories, the fundamental ingredients of reality are not point-like particles, but tiny vibrating strings, loops, or surfaces. Their vibrations determine the masses and charges of particles, the behavior of forces, and even the properties of space-time. For these vibrations to be mathematically consistent, they must occur in more dimensions than we perceive. Some versions require 10 dimensions, others 11. The extra dimensions are not visible because they may be curled up hidden, or spread across scales far beyond direct detection. Within this framework, our universe may be a 3-dimensional surface embedded in a higher dimensional space. This surface is called a brane, short for membrane. Everything we observe, matter, light, the motion of planets, the glow of galaxies, may be confined to this brane. Particles and forces that govern ordinary matter cannot leave it. They move along the surface, never drifting into the higher dimensional realm. Yet gravity appears to behave differently. It may spread into the surrounding dimensions, which could explain why gravity is so much weaker than the other forces. If space-time is a brane, and if branes can move, bend, or collide, then the origin of our universe may be far stranger than a simple expansion from a dense state. This idea leads to one of the most dramatic hypotheses in cosmology, that the Big Bang was the result of a collision between branes. In this picture, our universe and another brane existed parallel to each other in a higher dimensional space. They drifted, approached, and eventually struck. The collision released an enormous amount of energy, heating the brane and filling it with matter and radiation. This moment corresponds to what we perceive as the Big Bang. Space within the brane expanded, galaxies formed, and cosmic evolution unfolded. Meanwhile, the branes moved apart, cooling the universe as expansion continued. In this model, the Big Bang is not a singularity, not a bounce, and not a spontaneous fluctuation. It is an impact. The elegance of this proposal lies in its ability to merge cosmology with theories of fundamental physics. It offers a mechanism for the beginning of our observable universe, while avoiding the infinities that plague classical models. It replaces the singularity with a physical event. It explains the uniformity of the cosmic microwave background by suggesting that the branes were smooth before the collision. It provides a natural scale for density and temperature at early times, and it links the birth of the universe to the structure of higher dimensions, giving cosmology a place within a broader theoretical landscape. But this vision carries unanswered questions. If the universe was formed by a collision, what set the branes in motion? What governs their trajectories? Do collisions occur repeatedly, leading to cycles on a higher dimensional stage? If so, does time extend beyond the collision? Or does each cycle have its own arrow? These questions show how brain cosmology shifts the mystery rather than resolving it. Instead of asking what happened before the Big Bang within our universe, we ask what happened in the higher dimensional space that surrounds it. The idea becomes even more intriguing when we consider the possibility that collisions might leave observable traces if the brains did not collide perfectly, if the impact occurred at an angle, or if ripples formed in the higher dimensional space. Then subtler symmetries might appear in the cosmic microwave background. Some researchers have searched for such signatures, exploring patterns that could distinguish a brain collision from a classical Big Bang. So far, no decisive evidence has emerged, yet the idea remains scientifically alive because its predictions are concrete. Its mathematics is grounded in established frameworks, and its implications reach beyond speculation. There is another consequence of this model. If brains exist, there may be others besides our own. They may float through higher dimensional space, sometimes drifting close, sometimes far apart. Some may collide, forming universes like ours. Others may never meet. This expands the multiverse idea into a geometric picture. Instead of bubbles in an inflating sea, we imagine sheet surfaces and higher dimensional currents. Our universe becomes one structure among many, not isolated, but part of a larger architecture. Still, the brain hypothesis depends on theories that have not yet been confirmed experimentally. String theory and its relatives remain mathematically rich, but direct evidence for extra dimensions is still absent. Particle accelerators have not detected signatures of strings. Cosmological surveys have not revealed unmistakable traces of brain interactions. The framework remains compelling but unproven. It offers a pathway beyond the Big Bang, but not yet a definitive map. Even so, brain cosmology plays an essential role in our exploration, because it shows that the apparent beginning of the universe may be the consequence of dynamics occurring in a wider realm. It suggests that our universe might be a chapter in a story written across dimensions we cannot see, and it leads naturally to another provocative idea, one that proposes not collisions, cycles, or bounces, but the fading of time itself. In that vision, the universe does not repeat, rebound, or arise from a vacuum. Instead, it stretches into a distant future where particles dissolve, structures vanish, and the very meaning of scale disappears, allowing a new universe to begin. To step into that idea, we must move from brains and dimensions to a theory that redefines the flow of cosmic eras and claims that traces of previous universes may still be visible today. It is the next hypothesis in our journey, and it offers a view of reality in which the universe is not reborn through force fluctuation or collision, but through transformation. Among all the ideas that attempt to peer beyond the Big Bang, one stands apart for its boldness, and for the reputation of the mind that conceived it. Roger Penrose, one of the most influential mathematical physicists of the past century, proposed that the universe may pass through a sequence of eras he called Aons. In this vision, each eon begins with what we perceive as a Big Bang, and ends in a distant future where matter has decayed, black holes have evaporated, and only massless particles such as photons remain. In such a future, scale loses meaning. Without mass, there is no way to measure time or distance. In this strange condition, Penrose argues the universe becomes conformally equivalent to the state that existed at the Big Bang. The end of one aeon becomes mathematically identical to the beginning of the next. The universe is reborn not through collapse, collision, or fluctuation, but through the fading away of structure and the dissolution of time itself. This idea, known as conformal cyclic cosmology, transforms our understanding of cosmic history. Instead of imagining the universe emerging from a singularity, a bouncer-brain collision, or a vacuum fluctuation, Penrose suggests that the universe transitions smoothly from one aeon to the next through a transformation of scale. The geometry of space-time is stretched in such a way that the remote future maps onto a new beginning. The ultimate decay of matter, instead of signaling an ending, becomes the gateway to a new origin. Time does not loop or repeat, but flows through a succession of aeons, each with its own expansion, its own galaxies, and its own evolution. One of the most striking aspects of this hypothesis is that Penrose claims it could leave detectable traces in the present universe. If events such as the evaporation of supermassive black holes occurred in the previous aeon, their effects might imprint subtle patterns in the cosmic microwave background. These imprints would take the form of concentric circles regions of anomalously low temperature variation. Penrose and collaborators have claimed to identify such circles in observational data, suggesting that we may be seeing evidence from before the Big Bang. However, other researchers have challenged these findings, arguing that the observed patterns fall within the expected statistical noise of random fluctuations. The debate remains unresolved, reflecting both the ambition of the idea and the difficulty of extracting definitive signals from the delicate texture of the cosmic background. Even without confirmed evidence, conformal cyclic cosmology has drawn attention because it offers a radically different approach to the problem of beginnings. It avoids the singularity without invoking quantum gravity. It sidesteps the multiverse without relying on inflation. It removes the need for prior cycles driven by contraction and expansion. Instead, it proposes that the structure of space-time itself allows the end of one universe to seed the next. This approach reframes the question of origin as a question of symmetry. If the geometry of the universe becomes scale-free in the far future, then that geometry can be transformed into the beginning of a new aeon. The Big Bang becomes not a birth but a continuation. Yet the hypothesis introduces new puzzles. If each aeon contains galaxies, stars, and black holes, what determines the conditions at the start of the next aeon? If information survives the transition, how much of it influences the structure of the new universe? If information does not survive, then in what sense does the prior aeon matter? There are also questions about entropy. In thermodynamics, entropy tends to increase. Yet Penrose proposes that entropy resets through the loss of mass and the dissolution of structure. Critics argue that this violates fundamental principles. Supporters counter that the removal of mass and the conformal rescaling change the meaning of entropy itself. The debate touches not only on cosmology but on the foundations of physics. What makes the idea compelling is not that it answers every question, but that it challenges the assumption that the Big Bang marks the beginning of time. It suggests that time extends through a sequence of aeons, each separated not by destruction or emergence but by transformation. It proposes that the universe is older than we imagine, not through cycles of collapse and rebound, but through a chain of eras linked by geometry. And it raises the astonishing possibility that faint echoes of a previous universe may exist in the sky waiting to be interpreted. As with all the hypotheses we've explored, conformal cyclic cosmology remains speculative. It rests on assumptions about the fate of matter, the nature of space-time, and the behavior of black holes at unimaginable scales. It stands at the edge of observation where data is fragile and interpretations diverge. Yet it occupies an essential place in our exploration, because it reveals that the question of what came before the Big Bang can be answered in ways that do not rely on familiar concepts such as collapse causation or origin. It invites us to think of the universe not as a singular event, but as a sequence of eras connected by deep mathematical relationships. This brings us to the central turning point of our journey. We have now examined hypotheses that propose no, before hypotheses that propose cycles, hypotheses that propose bounces, hypotheses that propose fluctuations, hypotheses that propose multiverses, hypotheses that propose collisions, and hypotheses that propose aeons. Each of them challenges the conventional view. Each of them attempts to move beyond the singularity. Each of them reveals a different way in which the Big Bang may not have been the true beginning. In the next stage, we must step back and ask a deeper question. How can we distinguish among these possibilities? What evidence can we gather? What observations can we make? And how do we navigate the boundary between imagination and science? The exploration now shifts from hypothesis to evaluation, from possibilities to constraints. The universe may be older, larger or stranger than we once believed, but to find out we must confront the limits of what can be known, standing before 7 different visions of what might lie beyond the Big Bang. We now face a challenge that separates scientific exploration from speculation. How could any of these ideas be tested? Theories gain strength not through elegance, imagination, or philosophical appeal, but through contact with the observable world. A hypothesis becomes part of science only when it makes predictions that can in principle be confirmed or ruled out. This is especially demanding when dealing with events that took place at energies far beyond anything achievable on Earth, and at times earlier than any light we can observe. Yet cosmology has a remarkable advantage. The universe itself preserves records of its own past. Fossils of ancient physics are imprinted in radiation structure and geometry. To evaluate the possibilities beyond the Big Bang, we must learn to read those fossils. The most important of these records is the cosmic microwave background, the faint afterglow that fills the sky with astonishing uniformity. Tiny variations in its temperature reveal the earliest fluctuations that later formed galaxies and clusters. The pattern of these fluctuations acts as a map of the infant universe, showing how matter clumped, how space curved, and how energy behaved. Some hypotheses predict specific signatures in this map. A brane collision might leave directional asymmetries. A cyclic model might produce repeated patterns. A prior eon might imprint concentric rings of unusual smoothness. Yet searches for these signals have produced mixed results. Some studies report intriguing anomalies, others find no statistically significant features. The ambiguity reflects both the subtlety of the phenomena and the difficulty of extracting definitive meaning from data that is nearly uniform. Another observational window lies in gravitational waves. Unlike light, gravitational waves can pass through regions of extreme density without being erased. If the Big Bang was a bounce, a collision, or a transition from a prior phase, it might have generated a primordial background of gravitational waves. Detecting such a background would open a direct channel to the earliest moments of the universe. Experiments such as space-based detectors and pulsar timing arrays are being developed to search for these signals. If a distinct spectrum of primordial gravitational waves were found, it could eliminate some hypotheses and support others. Yet detection remains elusive, and the interpretation of any future signal will require caution. The large-scale structure of the universe also offers clues. The distribution of galaxies across cosmic space reveals how matter clustered over billions of years. This clustering depends on the conditions present near the beginning of cosmic time. Models that propose pre-Big Bang phases may predict subtle differences in the statistics of structure formation. Surveys that map millions of galaxies may reveal fingerprints left by earlier epochs. But once again, the signals are faint, buried beneath the noise of cosmic evolution. Extracting them demands both precision and patience. Even particle physics plays a role. Some hypotheses require new particles or fields that affect the early universe. Others imply specific relationships between energy scales, symmetry breaking, or the behavior of matter under extreme conditions. Experiments at the frontiers of high-energy physics may provide indirect support or constraints. The discovery of certain particles could strengthen particular models. The absence of predicted phenomena could weaken them. Yet the gap between laboratory energies and cosmic energies remains vast. Particle physics alone cannot resolve the question, but it can help shape the possibilities. There is also a more subtle constraint: parsimony. A theory that introduces countless untestable assumptions risks stepping outside the scope of science. The multiverse interpretation of eternal inflation faces this challenge. If every possible outcome occurs somewhere, then prediction becomes meaningless. The measure problem. The difficulty of defining probabilities in an infinite ensemble remains unresolved. A hypothesis must offer more than narrative breadth. It must offer discriminating power. it must be capable of being wrong. This raises an uncomfortable truth. It may turn out that some aspects of what happened before the Big Bang are fundamentally inaccessible. The observable universe has a horizon, a limit beyond which light has not had time to reach us. The finite speed of light and the expansion of space place hard boundaries on what we can see. Some information was erased during the earliest phases of the universe. Some signals may be forever beyond detection. This does not mean that inquiry must stop. It means that science must navigate between imagination and evidence, between what could be true and what can be known. Even so, the search continues, driven by technological advances, theoretical insights, and the inherent human desire to understand origins. New telescopes, new detectors, and new methods of analysis may yet reveal hints that distinguish one hypothesis from another. A subtle pattern in the microwave background, a whisper of primordial gravitational waves, an unexpected alignment in the geometry of space, any of these could reshape our understanding of cosmic history. As we move deeper into this final phase of our journey, we confront the ultimate questions. Are we capable of discovering what came before the Big Bang? Are the clues hidden in the sky waiting to be found? Or are we pressing against the limits of human knowledge, asking questions that the universe itself prevents us from answering? These questions lead us forward not into resignation, but into a clearer understanding of what it means to explore the cosmos scientifically. In the next part, we will examine those limits directly. The boundaries imposed by the horizon of the observable universe, by the nature of measurement, and by the structure of space-time itself. To understand what might lie beyond the Big Bang, we must first understand the edges of what can be known. To understand the limits of what can be known about the universe before the Big Bang, we must first confront a profound reality. We do not observe the universe as it is, but as it was. Light takes time to travel, and the farther we look into space, the farther we look into the past. When we observe distant galaxies, we see them as they were billions of years ago. When we study quasars, we witness a young universe filled with blazing structures that no longer exist. And when we examine the cosmic microwave background, we are looking back almost as far as light can carry information, to a time when the universe was still opaque plasma. This boundary forms what cosmologists call the surface of last scattering the earliest light we can detect. Beyond it, the universe becomes hidden not because it was empty, but because light could not yet travel freely. This limit creates a kind of cosmic curtain. We know that the universe existed before the release of the microwave background, but we cannot observe that period directly with the electromagnetic radiation. Everything earlier must be inferred indirectly from models, from relic particles, or from theoretical extrapolation. The curtain becomes even thicker as we approach the moment where our current physics ceases to apply. No telescope, no matter how powerful, can look beyond that boundary using light alone. The question of what happened before the Big Bang requires us to use different tools, because the universe has erased or concealed the signals that would otherwise reveal its earliest phase. Gravitational waves offer one potential window beyond this curtain. Unlike light, gravitational waves do not scatter off matter in the early universe. They travel through dense plasma without being absorbed. If the universe experienced a bounce, a collision, or a transition from a previous phase, gravitational waves might have been generated in abundance. These primordial waves could still exist today, stretched to long wavelengths by billions of years of expansion. Detecting them would provide a direct glimpse into the pre-Big Bang epoch. Yet the instruments required to observe such signals are still being developed. Ground-based detectors are sensitive to waves generated by black hole mergers, not to primordial echoes from the earliest moments of cosmic history. Space-based observatories and pulsar timing arrays may eventually reach the necessary sensitivity, but for now the evidence remains beyond our grasp. Another boundary arises from the expansion of space itself. The universe is stretching and distant galaxies recede from us faster over time. At great enough distances, the expansion becomes so rapid that light emitted now will never reach us. This defines the cosmic event horizon, a limit beyond which information cannot travel to the observer, no matter how long we wait. The event horizon is not a physical wall, but a mathematical condition imposed by the accelerating expansion of space. It means that vast regions of the universe are forever inaccessible. If the universe is part of a multiverse, if other bubbles exist beyond our cosmic boundary, or if traces of prior cycles lie outside our horizon, then we will never observe them. The universe imposes a fundamental limit on what can be seen. Even within the observable universe, quantum uncertainty places constraints on what can be known. At the smallest scales, the laws of physics do not allow perfect precision. Energy fluctuates, particles appear and disappear, and the geometry of space-time itself becomes uncertain. If the universe once existed in a quantum state before expanding, then its earliest configuration may be unknowable in principle. The concept of a definite history gives way to probabilities, amplitudes, and superpositions. In such a realm, asking what precisely happened before the Big Bang may be like asking where a particle was before it was measured. The question assumes a certainty that nature does not provide. These boundaries, cosmic, observational, and quantum, define the frontier of cosmology. They do not tell us that the question of what came before the Big Bang is meaningless. They tell us that answering it requires creativity, caution, and a willingness to accept uncertainty. Some aspects of the universe may be forever hidden, yet others may reveal themselves through indirect evidence. A subtle pattern in the cosmic microwave background, a faint signature in gravitational waves, or an unexpected deviation in the distribution of galaxies could illuminate the shadowed region beyond the limits of current theory. But there is a deeper insight hidden in these constraints. The limits of observation do not merely restrict what we can know. They teach us something about the structure of the universe itself. The fact that there is a surface of last scattering tells us that the early universe was once hot and opaque. The existence of an event horizon tells us that space is expanding and accelerating. The presence of quantum uncertainty tells us that space-time is not infinitely precise. These limits are not walls to despair against. They are clues. They are evidence of the physics that shape the cosmos. They guide us toward theories that extend beyond the boundaries of direct observation. As we continue exploring these frontiers, we must acknowledge a possibility that is both humbling and inspiring. The universe may be structured in such a way that some truths remain beyond reach, yet the pursuit of those truths drives science forward. The search for what came before the Big Bang is not only a quest for origin, it is a quest to understand the laws that govern time, space, and existence. And it leads naturally to a final question: why does the question itself matter? What do we gain by asking it? What does it reveal about us as creatures who look up and wonder whether the universe had a beginning, and whether that beginning had a story before it? In the next part, we will explore why the search for a pre-Big Bang reality continues even in the face of uncertainty, and why the question remains one of the most powerful forces driving human curiosity. Why does the question of what came before the Big Bang continue to pull at the human mind even when evidence is scarce and certainty may be forever out of reach? Part of the answer lies in the nature of science itself. Science does not advance by accepting the boundaries of current understanding. It advances by pressing against them. The history of cosmology is a record of horizons expanding. Once the Milky Way was believed to encompass all of existence. Then other galaxies were discovered, revealing a universe far larger than imagined. Later, the expansion of space was uncovered, transforming the static cosmos into a dynamic one. Then came the realization that the universe had a hot, dense past leading to the Big Bang model. Each step widened the frame. Each step showed that reality is bigger, older, and stranger than intuition suggests. The question of what came before the Big Bang is the next horizon in this sequence. It is the place where discovery may unfold. Yet the question reaches beyond science into something more personal. Human beings are storytelling creatures. We seek origins of families, of nations, of life, of worlds. A beginning provides structure, meaning, and context. It gives us a way to anchor ourselves in time. The Big Bang, for all its power, offers a beginning without a deeper story. It describes a moment of expansion but not what led to it. It presents a boundary but not a cause. For many, this feels incomplete. The desire to know what came before is not simply curiosity. It is an instinct to place ourselves within a narrative that extends beyond the visible frame. There is also a philosophical dimension that shadows the question, asking what happened before the Big Bang touches on the nature of causation. Every event we observe has a cause, every change has a prior condition. Our minds are shaped by a world in which causes flow into effects. The idea of a first moment with no prior cause conflicts with that pattern. Even when science shows that causation may break down at the origin of space-time, the instinct remains. We want the chain to continue. We want the story to stretch further back. This impulse is neither foolish nor unscientific. It has fueled breakthroughs throughout history. It was the refusal to accept the motionless Earth that led to celestial mechanics. It was the refusal to accept a static universe that revealed cosmic expansion. The refusal to accept the Big Bang as the ultimate beginning may lead to the next revolution. But there is another reason the question persists, and it lies in the nature of wonder. The night sky has always stirred a sense of awe. Long before telescopes, long before mathematics, long before physics, humans looked upward and felt the pull of the infinite. The stars did not answer, yet the longing to understand remained. Modern cosmology is built on equations, observations, and measurements, but beneath its analytical surface lives the same ancient feeling. The question of what came before the Big Bang is a modern expression of a timeless yearning, the desire to know whether the universe is bounded or boundless, whether time is finite or eternal, whether existence has a root or stretches without origin. Even so, the pursuit must remain disciplined. Scientific wonder differs from mythic wonder because it demands evidence. It requires that ideas be confronted by observation. It insists that belief bow to measurement. The danger is not in asking what came before the Big Bang, but in mistaking imagination for knowledge. Some hypotheses may never be testable. Some narratives may remain poetic rather than scientific. Recognizing this boundary is part of intellectual maturity, yet refusing to explore possibilities would be a betrayal of the spirit that drives discovery. The persistence of the question reveals something else. The unity of human curiosity. Cosmology, physics, philosophy, and even art converge here. The question touches identity, purpose, and scale. It invites humility by reminding us that our understanding is provisional. It invites ambition by suggesting that greater understanding is possible. It invites reflection by revealing how deeply our minds seek connection to the cosmos. And it invites caution by reminding us that some answers may lie beyond observation. Still, the search continues not only because we want answers, but because the pursuit reshapes the questions themselves. As theories evolve, as instruments improve, as data accumulates, the boundary of the knowable shifts. What was once thought inaccessible becomes measurable. The cosmic microwave background was invisible until technology caught up. Gravitational waves were theoretical until detectors confirmed them. Exoplanets were speculation until telescopes revealed thousands. The history of science is filled with things once believed unknowable. The greatest reason the question endures, then, is that it may yet yield insight, somewhere in the faint texture of the cosmic background, somewhere in the hum of gravitational waves, somewhere in the mathematics of space-time. A clue may exist that points beyond the Big Bang. The search is not a rejection of science, but an extension of it. To ask what came before is to assert that the universe has more to teach. In the next part, we turn towards synthesis. We will gather the threads of the 7 hypotheses, examine what unites them, what divides them, and what each reveals about the nature of time, causation, and existence. The journey's not ending. It is folding into a deeper exploration, one that seeks not only what might have happened before the Big Bang, but what that possibility means for our understanding of the universe itself. Now that we have travelled through 7 different visions of what may have preceded the Big Bang, a new phase of understanding emerges not by choosing one hypothesis over another, but by examining the deeper themes that run through them. Each model, despite its differences, attempts to answer the same core puzzle. Why do our current theories fail when we trace the universe back to its earliest moments? The singularity is not an explanation but a signpost. It tells us where our equations break, where our assumptions crumble, and where new physics must begin. The 7 hypotheses are not competing myths. They are attempts to repair the fracture, each proposing a different way to extend the structure of reality beyond the visible edge. One of the unifying themes is the role of time. In the first hypothesis, time begins with the universe. In the cyclic and bounce models, time flows through prior eras. In the multiverse vision, time may exist separately within each bubble. In the brain collision picture, time may belong to a higher dimensional arena. In conformal cyclic cosmology, time stretches through successive eons. These differences reveal something profound. Our understanding of time is not settled. Time may be emergent, directional, cyclic, finite, or scale-dependent. The question of what came before the Big Bang is therefore inseparable from the question of what time is. If time depends on space-time geometry, then its origin may be a feature of cosmology, not metaphysics. If time emerges from deeper processes, then the Big Bang is not the first moment, but the first moment in which time becomes meaningful. Another theme concerns the structure of space-time. In the classical Big Bang model, space-time is continuous and smooth, until it reaches the point where the equations diverge. In the quantum bounce model, space-time is discrete, composed of finite units. In brain cosmology, space-time is a surface embedded in higher dimensions. In the multiverse picture, space-time is divided into disconnected regions. In conformal cyclic cosmology, space-time can be rescaled to bridge the gap between aeons. These perspectives suggest that space may be more than a passive arena. It may have texture-shaped dimensionality and behavior that change under extreme conditions. The idea that space might emerge, dissolve, or transform challenges the intuition that space is simply where things happen. Instead, space may be one of the things that happens. Causation also undergoes reinterpretation. In everyday experience, causes precede effects in a linear chain. But if time begins at the Big Bang, causation cannot extend earlier. If the universe rebounds, causation may pass through a transition. If the universe forms from a fluctuation, causation may arise from probability. If the universe emerges from a collision, causation may belong to higher dimensional dynamics. If the universe transitions through aeons, causation may be preserved through geometric continuity. These models show that causation is not a fixed concept. It may depend on the structure of time, the nature of space-time, and the domain in which laws apply. Asking what caused the Big Bang assumes a framework that may fail at that boundary. Yet despite these reinterpretations, all 7 hypotheses share another common feature. They attempt to keep the universe within the scope of science. None of them invoke supernatural forces, mystical origins, or metaphysical absolutes. They rely on mathematics symmetry, quantum principles, field theory, or geometric structure. They attempt to replace the singularity not with mystery but with mechanism. This is a remarkable convergence. It shows that the pursuit of what came before the Big Bang is not a departure from science, but an extension of it. At the same time, each hypothesis carries limitations that reveal the challenges ahead. The know-before model lacks explanatory depth. The cyclic and bounce models struggle with entropy and information. The vacuum fluctuation idea depends on uncertain quantum foundations. Eternal inflation faces the measure problem and observational inaccessibility. Brain collisions depend on unverified extra dimensions. Conformal cyclic cosmology rests on assumptions about the remote future that cannot yet be tested. Each model solves some problems while creating others. None is complete. None has definitive evidence. None yet commands consensus. Rather than signaling failure, this diversity reflects the richness of the problem and the frontier nature of the inquiry. These themes together shape a new understanding of the question itself. Asking what came before the Big Bang is not simply a search for a prior state. It is a doorway into deeper issues: how time emerges, how space-time behaves, how causation operates, how physical laws originate, and how far observation can reach. The question persists not because we lack imagination, but because the universe invites it. The singularity is the point where our theories surrender. The hypotheses are attempts to reclaim the territory, and the synthesis reveals that the true mystery is not what happened before, but how to describe a reality in which before may not exist in the way we assume. As we move forward, the journey enters its final arc. We will examine how these themes shape our understanding of the universe, how they influence the meaning of beginnings, and how they reshape the connection between humanity and the cosmos. The exploration is no longer about selecting a single answer, but about recognizing that the universe may be stranger, deeper, and more layered than any single model can express. The Big Bang may not be the first page. It may be the first page we can read. In the next part, we'll turn toward what these possibilities mean for the future of cosmology, how theories may evolve, what discoveries may shift the landscape, and how the quest to understand what came before the Big Bang may guide the next generation of scientific breakthroughs. The future of cosmology will be shaped by how we pursue the question of what came before the Big Bang, and by the tools we develop to investigate the earliest moments of the universe. The next breakthroughs are unlikely to come from a single discipline. They will emerge from the intersection of astronomy, particle physics, quantum theory, gravitational research, and data analysis on unprecedented scales. The mysteries at the edge of time demand instruments capable of probing deeper than light, can reach theories capable of unifying the large with the small, and methods capable of extracting meaning from signals that are faint, ancient, and easily erased. To imagine how the coming decades may reshape our understanding, we must look at the frontiers now forming around us. One frontier lies in the study of gravitational waves. The detection of these ripples in space-time confirmed a prediction of general relativity and opened a new window into the universe. So far, the waves we have observed come from collisions of black holes and neutron stars events that occurred long after the Big Bang. But future detectors, including space-based observatories and networks that measure subtle variations in pulsar timing, may be sensitive enough to detect the primordial gravitational wave background. If such a signal exists, it could carry information from before the release of the cosmic microwave background. It could reveal whether inflation occurred, whether a bounce preceded expansion, or whether the early universe was shaped by processes unknown today. A single detection could eliminate entire classes of hypotheses and strengthen others. The possibility electrifies the field. Another frontier lies in high-precision mapping of the cosmic microwave background. Current measurements already reveal temperature variations with astonishing accuracy, but future missions aim to detect even finer details, including polarization patterns that might encode signatures of primordial gravitational waves. If such patterns are found, they could serve as a fingerprint of the earliest physics. They might reveal whether inflation happened, whether the universe emerged from a prior phase, or whether subtle imprints from an earlier Aeon remain. Conversely, the absence of such patterns would challenge inflationary models and shift attention toward alternatives such as conformal cyclic cosmology or quantum bounce scenarios. Data will sharpen the debate. Large-scale galaxy surveys represent a third frontier. As telescopes map millions of galaxies across billions of light-years, patterns in the clustering of matter become clearer. These patterns depend on the initial conditions of the universe. If the early cosmos contained asymmetries, non-Gaussian fluctuations, or signatures from a previous era, they might appear in the distribution of galaxies. The structure of cosmic voids, filaments, and superclusters could hold clues to physics beyond the Big Bang. New instruments will extend this mapping deeper into space and further back in time, pushing closer to the era where the first gravitational seeds were planted. A fourth frontier emerges from particle physics and quantum theory, experiments that probe the nature of dark matter. The properties of neutrinos or the behavior of quantum fields may indirectly reveal information about the early universe. If dark matter consists of particles formed before the Big Bang, they could carry information from a prior phase. If symmetries break in specific ways, they could support or refute particular cosmological models. And if quantum gravity develops into a complete theory, it may finally explain how spacetime behaves at the smallest scales, removing the singularity and showing whether time extends beyond it. The unification of general relativity and quantum mechanics remains one of the greatest goals in physics, and cosmology sits at its crossroads. A fifth frontier lies in computational power. The early universe cannot be recreated in a laboratory, but it can be simulated. Advances in numerical modeling, machine learning, and data interpretation allow researchers to explore scenarios that were once impossible. Simulations can test how galaxies would form under different initial conditions, how gravitational waves would propagate through a bouncing universe, or how brain collisions might leave observable traces. As computational tools grow stronger, the boundary between theory and testable prediction narrows, yet the most profound frontier may be philosophical in the scientific sense. Cosmologists must grapple with what it means for a theory to be testable when dealing with conditions beyond direct observation. They must decide how to treat hypotheses that produce indirect clues, probabilistic arguments, or predictions that may only be observable in principle. The history of science shows that boundaries of testability shift. Once atoms were considered unobservable, once black holes were regarded as mathematical curiosities, once gravitational waves were dismissed as undetectable. The question is not whether the pre-Big Bang universe is forever inaccessible, but whether the tools of the future will stretch far enough to reach it. These frontiers suggest that the coming era of cosmology will be defined not by final answers, but by expanding possibilities. The debate will not narrow, it will deepen. Some hypotheses may gain support, others may fade. New ideas may emerge combining elements from multiple theories. The concept of a single origin may dissolve into a richer understanding of cosmic history. Time itself may be redefined. Space may be reconceived. Causation may be reframed. The universe may appear less like a singular story, and more like a tapestry woven from overlapping layers of physics, geometry, probability, and emergence. The search for what came before the Big Bang is therefore not only about the past, it is about the future of science. It shapes the kinds of instruments we build, the questions we ask, the mathematics we develop, and the way we interpret reality. It reminds us that the greatest discoveries often arise where certainty falters. It reveals that ignorance is not a void but a frontier. In the next part, we will step toward the emotional culmination of the journey, how these ideas reshape our place in the universe, what they reveal about human curiosity, and how the search for origins becomes a reflection of who we are as a species that looks backward in time to understand where we came from, and forward in wonder to imagine where knowledge may lead. As we draw nearer to the emotional horizon of this journey, the focus shifts from the universe itself to the beings who dare to question it. For all the mathematical rigor, observational discipline, and theoretical imagination involved in exploring what came before the Big Bang, there remains a deeper truth. The search reveals as much about humanity as it does about the cosmos. No other species has looked at the night sky and wondered whether time had a beginning. No other mind has imagined universes beyond its own. The question is a mirror. It reflects our capacity for abstraction, our hunger for meaning, and our refusal to accept the limits imposed by scale, distance, or duration. When we contemplate a universe that may have existed before ours, we confront our own smallness in a way that is both humbling and exhilarating. Earth becomes a grain of dust in a galaxy among billions itself, a minor feature of a universe that may be only one bubble among countless others, and yet within this immensity consciousness has arisen. Atoms forged in stars have arranged themselves into brains capable of imagining origins beyond visibility. The same universe that makes us insignificant also grants us the ability to understand its laws. This paradox forms one of the most extraordinary features of existence. The cosmos produces minds capable of comprehending the cosmos. The search for what came before the Big Bang also reveals something about the human relationship to uncertainty. Most animals fear the unknown. Humans pursue it. We build instruments to see farther. We derive equations to describe what cannot be touched. We peer into darkness not to flee but to illuminate. Even when answers remain elusive, the act of seeking reshapes our understanding. The horizon of knowledge advances, and with it our sense of identity. We become participants in a story that stretches beyond generations, beyond epochs, beyond the lifespan of stars. The search binds us to the universe in a way that transcends physical scale. There is another dimension to this exploration, the sense of wonder that persists even in the face of incompleteness. Some may believe that science diminishes mystery, replacing awe with cold description. Yet the opposite is true. The more we discover, the more astonishing the universe becomes. It is not less wondrous to learn that time may have emerged from quantum geometry. It is not less magnificent to imagine worlds forming in an endless inflationary sea. It is not less poetic to consider eons rising from the ashes of evaporated black holes. Knowledge does not extinguish wonder. It deepens it. This is why cosmology resonates beyond laboratories and observatories. It touches the language of art, poetry, myth, and philosophy, not because it replaces them, but because it shares their subject. The universe is the oldest story written in light, matter, and space-time. Humans have always sought to read it first through constellation myths, later through telescopes, and now through gravitational detectors and quantum mathematics. The search for what came before the Big Bang is the latest chapter in that story. It is science, but it is also a continuation of an ancient impulse to understand where we come from and where we belong. Yet the pursuit carries a responsibility. As the universe grows larger in our understanding, humanity must grow more humble. We are not the center of creation. We are not the purpose of cosmic unfolding. We are observers, transient and fragile, living in a brief moment of cosmic time. And yet that transience gives our curiosity weight. The fact that finite beings can contemplate the infinite gives our existence a kind of meaning that does not depend on centrality. We matter not because the universe was made for us, but because we strive to understand it despite our smallness. There's also a unity in this search. Across cultures, languages, and eras, humans have wondered about beginnings. The vocabulary changes, but the impulse does not. Ancient astronomers tracked the motions of planets. Philosophers pondered eternity. Today, researchers analyze cosmic backgrounds and quantum fields. Different tools, same yearning. The question of what came before the Big Bang reveals that humanity shares a common inheritance: curiosity. As we approach the closing arc of this script, a final realization emerges. The journey to understand what preceded the Big Bang is not merely about answering a scientific question. It is about recognizing that the universe is not static, finished, or fully revealed. It is dynamic, evolving, and partially hidden. And our understanding of it is dynamic as well. We are participants in a process that expands knowledge generation after generation. The frontier does not end, it shifts. In the next part, we will move toward the emotional and intellectual conclusion of this exploration. How the search for a pre-Big Bang reality changes our view of existence, how it reframes the meaning of beginnings, and how it invites us to live with wonder in a universe that may have existed long before us and may continue long after memory, matter, and even time have faded. Reaching the end of this journey, we find ourselves looking not only backward toward the origins of the universe, but inward toward the meaning of beginnings themselves. The question of what came before the Big Bang has carried us through theories of emerging time, eternal cycles, quantum rebounds, multiverse bubbles, higher dimensional collisions and aeons that fade into one another through the dissolution of scale. Each possibility expanded the frame of reality. Each revealed that the boundary we once believed was absolute may instead be a horizon of understanding. And now, with the full sweep of these ideas behind us, a final insight comes into view. Beginnings are not singular points. They are perspectives. The Big Bang remains the earliest moment for which we have clear evidence. It marks the origin of the observable universe, the release of the cosmic microwave background, and the unfolding of cosmic structure. But whether it was the first moment of time, the aftermath of a prior collapse, the birth of a bubble universe, the result of a brain collision, or the start of a new aeon, depends on how we define origin itself. A beginning may be the point where our equations apply. A beginning may be the point where information becomes accessible. A beginning may be the point where time becomes meaningful. In this sense, the Big Bang is less a starting line, and more the earliest point at which the universe becomes readable. This realization reshapes how we think about the cosmos. It suggests that the universe may not have a single origin, but multiple layers of origin, each defined by a different scale of understanding. On the human scale, origin lies in the formation of Earth and the emergence of life. On the planetary scale, origin lies in the birth of stars. On the cosmic scale, origin lies in the Big Bang. And beyond that origin may lie in processes we do not yet have the language to describe. The question of what came before the Big Bang therefore becomes a question about where we choose to anchor the story. Yet this does not diminish the scientific pursuit. Instead, it makes it richer. The recognition that beginnings depend on perspective invites deeper inquiry, not resignation. It honors the complexity of the universe rather than forcing it into a single narrative. It reminds us that science evolves and that the definitions we use today may be replaced by more profound understandings tomorrow. The Big Bang was once an unthinkable idea. Now it is a foundation. The hypotheses that extend beyond it may one day stand in the same position. This perspective also changes how we see ourselves. If the universe is part of an endless sequence, a multiverse, a higher dimensional architecture, or a chain of eons, then our existence becomes part of a grand continuum. We are temporary arrangements of matter in a universe that may have existed long before us, and may continue long after the last star has faded. But rather than diminishing our significance, this awareness highlights a remarkable truth. For a brief moment, the universe knows itself through us. The atoms of our bodies were forged in ancient stars. The neurons of our minds reflect electrical patterns shaped by physical laws. When we contemplate the origins of the universe contemplates itself. In this light, the search for what came before the Big Bang becomes a celebration of consciousness. It is a reminder that curiosity is one of the rarest and most extraordinary phenomena the universe has produced. The cosmos may be vast, ancient, and indifferent, yet we respond to it with wonder. We ask questions that stretch beyond our lifespan, beyond our planet, beyond our epoch. We build instruments to collect photons that have travelled billions of years. We record signals so faint they barely disturb space. We construct theories that reach into dimensions we cannot see. These acts are expressions of something profound, the will to understand. As this journey comes to a close, one final reflection remains. The universe does not need us to ask where it came from, yet we ask. The universe does not require observers, yet observers exist. The universe does not explain itself, yet we seek explanations. This tension between silence and inquiry is the essence of the human experience. We live briefly in a universe that may extend infinitely, and during that brief time we choose to wonder. Perhaps the ultimate meaning of the question is not in the answer, but in the asking. Whether time began at the Big Bang or stretches beyond it, whether universes cycle, collide, branch, or dissolve, the act of seeking connects us to the cosmos in a way nothing else can. It turns existence into dialogue. It transforms the night sky from darkness into mystery. It gives our fragile lives a place in a story that spans scales beyond comprehension. The universe may have had a beginning or many beginnings. It may have existed forever or for a finite span. It may be one among countless universes or the only one that will ever be. We do not yet know, but we are learning, and the learning itself is a form of meaning. Our journey ends here, but the frontier remains. The question continues. The cosmos waits silent, but not mute patient, but not closed vast, but not unreachable. And somewhere in the space between knowledge and wonder, humanity stands looking outward, asking the oldest and newest question in existence. What came before?